We actually have a better map of the orbits around the supermassive black hole at the center of the Milky Way than we do of the deep oceans right here on Earth. There are massive animals living completely out of our sight. Take the colossal squid, for example, a creature so bizarre it looks entirely alien. And the blind spot we have regarding their habitat is huge. Water deeper than 1 kilometer covers more than 60% of the planet, making the deep abyss the most common environment on the globe. It's also incredibly hostile. Down there, animals have to survive in perpetual darkness, near freezing temperatures, and a severe lack of both oxygen and food. But the most intense physical challenge is extreme hydrostatic pressure. Drop down just 1,000 meters, and the pressure is 100 times greater than what we experience at the surface. To understand exactly how extreme that is, this animated diagram shows a direct volumetric comparison. If you took the air inside a standard soccer ball down to that depth, the pressure would crush it down to the size of just 1.5 ping pong balls. Surviving in the most common environment on Earth requires some bizarre physical sacrifices. These animals have to build their bodies completely differently than surface life. For starters, standard fish anatomy is a lethal liability in the deep. Most surface fish rely on gas-filled cavities, like swim bladders, to maintain buoyancy. Down here, those bladders would instantly collapse. The evolutionary workaround is drastic. Super deep water fish often have minimal skeletons and jelly-like flesh. They actually use the surrounding water itself as their internal structural support. For a long time, sheer isolation protected them. But as coastal fisheries became depleted, the commercial fishing industry pushed into deeper, unknown waters. At first, this desperate expansion looked like a massive success. Fishermen found an untapped supply of large, unexpectedly tasty fish. But there is a brutal irony here. The precise biological traits that make these fish perfectly adapted to survive crushing physical pressure leave them completely defenseless against modern industrial fishing pressure. Living in freezing water with almost zero food means every biological process operates in slow motion. These fish grow slowly and they reproduce slowly. The poster child for this slow-motion biology is the Orange Roughy, a species that lives between 500 and 1,500 meters below the surface. Because their metabolism ticks along at such a slow rate, Orange Roughy often live for more than a century. This split-screen visualization compares the math. On side A, shallow water fish like cod replace 50% of their population yearly. On side B, the Orange Roughy replaces just 6% annually. Its rate is completely dwarfed. When you combine a century-long lifespan with a 6% reproduction rate, the math is unforgiving. Any mass removal of these fish becomes an irreversible loss on a human timescale. When commercial fishing for Orange Roughy took off in the 1980s, the initial catches were incredibly lucrative. Ships were pulling up unbelievable numbers of large fish. But biology eventually forces the math. Within just 25 years of the boom starting, those exact same deep-sea nets began coming up completely empty. If you harvest a natural resource that cannot quickly replenish itself, you are no longer fishing. You are effectively mining the ocean. This creates a dual tragedy. It guarantees the extinction of ancient, slow-growing ecosystems while simultaneously destroying the long-term livelihoods of the fishermen who depend on them. There is only one logical way out of this crisis. Commercial harvesting rates must be strictly capped to precisely match the biological replacement rates of the fish. We can always look to the cosmos and theoretically mine dead asteroids for minerals. But as far as we know, Earth is the only place in the universe with fish, so protecting them is a strict requirement for our future survival and our future cuisine.